This presentation is delivered by the Stanford Center for Professional Development.
Okay, so let's go into today's technical material. So, welcome back. What I want to do today is continue our discussion of principal components analysis of PCA, and in particular, there's one more application that I didn't get to in the last lecture on latent semantic indexing, LSI. And then I want to spend just a little time talking about how to implement PCA, especially for very large problems. And in particular, I'll spend just a little bit of time talking about the singular value decomposition, or the SVD implementation of principal component analysis. And then in the second half of today's lecture, I want to talk about a different algorithm called independent component analysis, which is in some ways related to PCA, but in many other ways is also also manages to accomplish very different things than PCA. And so with this lecture, this will actually wrap up our discussion on unsupervised learning, and the next lecture we'll start to talk about reinforcement learning algorithms. Okay, so just to recap where we were with PCA, right? Principal component analysis. I said that in PCA we imagine that we have some very high dimensional data that perhaps lies approximately on some low dimensional subspace. And so if you have a data set like this, you might find that that's the first principal component of the data, and that's sort of the second principal component of this 2D data. And to summarize the algorithm, right, we sort of had 3 steps. The first step of PCA was to normalize the data to 0 mean and unit variance. So subtract out the means of your training examples so it now has 0 means, and then normalize each of your features so that the variance of each feature is now 1. So it has unit variance. The next step was you then compute the covariance matrix of your 0 mean data. Right, so you compute it as follows. The sum of alter products, excuse me. And then you find the top k eigenvectors of sigma. Okay. So last time we saw a few applications of this. For example, one of the applications was to eigenfaces, where each of your training examples, xi, is itself an image. And so if you have, say, 100 by 100 images, if your pictures of faces are, say, 100 pixels by 100 pixels, then each of your training examples, xi, will be a 10,000 dimensional vector corresponding to the 10,000 grayscale intensity pixel values, right? The 10,000 pixel values in each of your 100 by 100 images. So remember, the eigenfaces application was where the training examples comprised pictures of faces of people, and then we ran PCA, and then to measure the distance between, say, a face here and a face there, we would project both of the face images onto the subspace, and then measure distance along the subspace. So for eigenfaces, you use something like 50 principal components. So the difficulty with working with problems like these is that in step 2 of the algorithm, when you construct the covariance matrix sigma, right, the covariance matrix now becomes a 10,000 by 10,000 dimensional matrix, which is huge, right? That's what? That's I guess that has 100 million entries, which is huge. And so we'd like to apply PCA to very, very high dimensional data because there's a point of reducing the dimension. But step 2 of this algorithm had this, step where you're constructing a ridiculous, so this extremely large matrix, which you sort of can't do. Come back to this in a second. It turns out one of the other maybe frequently used applications of PCA is actually to text data. So here's what I mean. You remember our vectorial representation of emails, right? So this is way back when we were talking about supervised learning algorithms for, say, spam classification. You remember I said that given a piece of email or given a piece of text document, you can represent it using a very high dimensional vector by taking, writing down the list of all the words in your dictionary, and so on, right? And somewhere you have the word like learn, somewhere you have the word study, and so on. And then depending on whether each word appears or does not appear in your text document, you put either 1 or 0 there, right? This is a representation we use in, like, I don't know, lecture 5 or lecture 6 for representing text documents for when we're building naive Bayes classifiers for text classification. And so turns out one of the common applications of PCA is actually to this sort of text data representations as well. And when you apply PCA to this sort of data, the resulting algorithm, it often just goes by a different name, which is latent semantic indexing. And for the sake of completeness, I should say that in LSI, you usually skip the pre-processing step. So for various reasons, in LSI, you usually don't normalize the mean of the data to 1, and you usually don't normalize the variance of the features to 1. But other than that, these are sort of relatively minor differences, it turns out. And so it does essentially the same thing, it does something very similar to PCA. Yeah. Normalizing the variance to 1 for text data would actually be a bad idea because all the words are, that would have the effect of dramatically scaling up the weight of rarely occurring words, right? So for example, the word aardvark hardly ever appears in any document. And so to normalize the variance of the feature, of the second feature to 1, you end up scaling up the weight of the word aardvark dramatically. So don't worry if you don't understand what I just said. So let's see. Say we're applying learning algorithms to language. Something that we want to do quite often is given 2 documents, xi and xj, right, to measure how similar they are. So for example, I may give you a document and say, can you please find me more documents that are like this one? So we're reading some news article about some news event of the day, and I want to find out what other news articles there are. So I'm going to give you a document and say, can you look at all my other documents I have in a large set of documents and find the documents most similar to this. And so this is a typical text application. And so to measure the similarity between 2 documents in xi and xj, where again, each of these documents is represented as one of these high dimensional vectors. One common way to do this is to view each of your documents as some very high dimensional vector. Right, so these are vectors in the very high dimensional space where the dimension of the vector is equal to the number of words in your dictionary. So maybe maybe each of these documents lives in some 50,000 dimensional space if you have 50,000 words in your dictionary. And so one measure of the similarity between these 2 documents that's often used is what's the angle between these 2 documents. Okay. Let's see. Right. And in particular, if the angle between these 2 vectors is small, then the 2 documents will consider them to be similar, whereas the angle between these 2 vectors is large, then we consider the documents to be dissimilar. And so more formally, one commonly used heuristic in natural language processing is to say that the similarity between two documents is a cosine of the angle theta between them, right? So for small values anyway, right, the cosine is a decreasing function of theta. So the smaller the angle between them, the larger the similarity. And the cosine between two vectors is, of course, just xi transpose xj divided by that's just the I don't know, the linear algebra or the sort of, you know, standard geometry definition of the cosine between two vectors, right? Here's the intuition behind what LSI is doing. Right. The hope, as usual, is that there may be some interesting axes of variations in the data, and there may be some other axes that are just noise. And so by projecting all of your data onto a lower dimensional subspace, the hope is that by running PCA on your text data this way, you can remove some of the noise in the data and get better measures of similarity between pairs of documents. Just let's delve a little deeper into this example to convey more intuition about what LSI is doing. And so let's look further in the definition of the cosine similarity measure, right? So the numerator of right. The numerator of the similarity between the two documents was this inner product, which is therefore sum over k xik xjk. Okay, and so this inner product will be equal to 0 if the two documents have no words in common, right? So this is really sum over k indicator of whether documents I and j both contain a word k, because I guess xik indicates whether document I contains the word k, and xjk indicates whether document j contains the word k. And so the product will be 1 only if, you know, the word k appears in both documents. And therefore, the similarity between these two documents will be equal to 0 if the two documents have no words in common, right? And so, for example, suppose your document xi, you know, has the word study and the word xj has the word learn, then these two documents may be considered entirely dissimilar, right? So we have a document about, you know, effective study strategies, right? Sometimes you read a news article about that, so you ask, well, what are the documents similar to this? Then if there are a bunch of other documents about, you know, good methods to learn, then there are no words in common, and so the similarity between these two documents is 0. So here's a cartoon of what we hope LSI or PCA will do, which is, suppose that on the horizontal axis, I plot the word learn, and on the vertical axis, I plot the word study. Okay, and so the values take on either the value 0 or 1. So if a document contains the words learn but not study, then, you know, plot that document there. And if a document contains neither the word study nor learn, I'll plot that at 0, 0. So here's a cartoon behind what PCA is doing, which is, we identify a lower dimensional subspace. That'll be some, you know, eigenvector we get out of PCA, called UI, say. And now, suppose we have a document about learning, we have a document about studying. The document about learning It's points to the right, document about studying points up. And so the inner product, or the cosine angle between these two documents will be 90 degrees, excuse me. So the inner product between these two documents, one on studying and one on learning, will be 0. And so it's as if these two documents are entirely unrelated, which is not what we want, right? Because documents on studying and documents on learning are related. But we take these two documents and we project them onto this subspace. Then these two documents now become much closer together. And the algorithm will recognize that when you take the inner product between these two documents, you actually end up with a positive number. And so LSI enables our algorithm to recognize that these two documents have some positive similarity between them. Okay? So that's just sort of intuition about what PCA may be doing to text data. And the same thing goes for other examples in the word study and learn, right? So you have, you find that a document about, politicians and a document now with the names of prominent politicians, you find that, right, that will also bring the documents closer together, or just any related topics may end up mapped to points that are closer together in this lower dimensional space. Okay. All right, there's questions about this?
That sum is over I or K?
Which one? The bottom.
Third line.
This one? This one?
No, the line.
Oh, this one. Oh, yes, thank you. Right. There's a little typo there. Right, let's have a okay. Okay. So, let's talk about how to actually implement this now. I'm curious, how many of you have seen, how many of you know what an SVD or singular value decomposition is? Wow, there's a lot of you. It's far more than I thought. Oh, curious, did you guys learn it as undergrads or as graduate students?
Grad.
Yeah, okay, cool. Yeah, all right. I think let me talk about it anyway. I think I wasn't expecting so many of you to know what SVD is, but I want to get this on tape just so that everyone else can learn a little bit about this too. So say a little bit about how to implement PCA. The problem I was alluding to just now was that when you have these very high dimensional vectors, then sigma is a large matrix. So in particular, for our text example, if the vectors xi are 50,000 dimensional, then the covariance matrix will be 50,000 dimensional by 50,000 dimensional, which is just much too big to represent explicitly, right? So, yeah, I guess many of you already. I guess many of you already know this, but I'll just say it anyway. So it turns out there's another way to implement PCA, which is turns out if A is any m by n matrix, then one of the most remarkable results of, I think, linear algebra is that the matrix A always has can be decomposed into a singular value decomposition. And what that means is that the matrix A, which is n by n, can always be decomposed into a product of three matrices, where U is n by n, D is a square matrix, which is n by n, and V is also n by n. And D is going to be diagonal. Okay, and with zeros on the off diagonals, and the values sigma I are called the singular values of the matrix A. So, yeah, I guess almost all of you said you learned this as a graduate student rather than as an undergrad. So it turns out that when you take a class in undergraduate linear algebra, you usually learn a bunch of decompositions. Like you usually learn about, I don't know, like the QR decomposition, maybe the LU factorization of matrices. Most undergrad courses don't get to talk about singular values decompositions, but at least in almost everything I do in machine learning, you actually find that you end up using SVDs much more than any of the decompositions you learned in like typical undergrad linear algebra class. So just personally, I've probably used an SVD, I don't know, dozens of times the last year, but LU and QR decompositions, I think I used a QR decomposition once and like an LU decomposition not at all in the last year. Right? So let's see. Let me say a bit more about this. So let me just draw the picture, I guess. So for example, if A is an n by n matrix, it can be decomposed into another matrix U, which is also n by n. It's the same size, D, which is n by n. And another square matrix, V transpose, which is also n by n. And so, and furthermore, in the singular value decomposition, the columns of the matrix U will be the eigenvectors of AA transpose, and the columns of V will be the eigenvectors of A transpose A. And to compute it, you just use the SVD command in, say, MATLAB or Octave. Okay? And so, today, state of the art in numerical linear algebra is that the SVD, singular value decompositions of matrices, can be computed extremely stably. And so you have used a package like MATLAB or Octave to compute, say, the eigenvectors of a matrix. And so I think I say that sort of SVD routines are even more numerically stable than eigenvector routines for finding eigenvectors in a matrix. So you can sort of safely use a routine like this. And similar to the way they use like a square root command without thinking about how to compute it, right? You can compute square root of something and just not worry about it. The computer will give you the right answer. For most reasonable size matrices, even up to thousands by thousands matrices, the SVD routine I think of as like a square root function in the sense that you can call it and it'll give you back the right answer and you sort of don't have to worry too much about it. If you have extremely large matrices, like a million by million matrices, I might start to worry a little bit, but you have like a few thousand by a few thousand dimensional matrices. This is implemented very well today. Yeah. What's the complexity of SVD? It's a good question. I actually don't know. I think it's on. I want to guess it's roughly on the order of n cubed, but I'm not sure. Yeah. It's usually an iterative algorithm, so I think it's. I don't know what's known about the convergence of these algorithms. Okay, so the example I drew out was for fat matrix. The matrix is wider than its tau. In the same way, you can also call SVD on a tall matrix. It's sort of taller than its wide, and it would decompose it into okay, a product of free matrices like that. And so, the nice thing about this is that we can use it to compute our eigenvectors in PCA very efficiently. In particular, our covariance matrix sigma was this. Right, it was the sum of all the products. And so if you go back and recall the definition of the design matrix. I think I described this in, what was it? I think it was lecture 2, when we derived a closed form solution to least squares, ordinary least squares. The design matrix was this matrix, right, where I take my training examples and stack them in rows, and I call this the design matrix denoted capital X, right? So if you construct the design matrix, then the covariance matrix sigma can be written just X transpose X, right? Well, right, that's X transpose, and I guess here's X. Okay. I don't know. I hope you see why the X transpose X gives you the sum of outer products of vectors. If you aren't seeing this right now, I don't know, when you go home and just convince yourself that this equality holds true. And so, to get the top k eigenvectors of sigma, right, you would take sigma and decompose it using excuse me. Right. You would take the matrix X and you compute as SVD, so you get U as V transpose. And then, the top k columns of U are the top k eigenvectors of X transpose X, which is therefore the top k eigenvectors of your covariance matrix sigma. Okay? And so in our examples, the design matrix may be, say, R. If you have 50,000 words in your dictionary, then the design matrix will be R M by 50,000. So maybe like, say, 100 by 50,000 if you have 100 training examples. And so X would be quite tractable to represent and compute the SVD of, whereas the matrix sigma would be much harder to represent. This is 50,000 by 50,000. So this gives you an efficient way to implement PCA. Yeah. So the reason I wanted to talk about this was, in previous years I didn't talk about SVD, and sort of in the class projects I found a number of students trying to implement SVD on huge problems and building these huge matrices. So this is sort of the much better way to implement PCA if you have extremely high dimensional data. If you have low dimensional data, if you have like 100 dimensional, if you have like 50 or 100 dimensional data, then computing sigma is no problem. You can do it the old way, but otherwise use the SVD to implement this. Okay. Questions about this? So the last thing I'll say is just in practice, when you want to implement this, I'm going to say sort of a note of caution. It turns out that for many applications of, let's see, when you apply SVD to these wide, yeah.
Sorry, just a quick question. Is it the top k columns of U or V, because X transpose X is V, dV transpose, right?
Oh, let's see. Oh yes, I think you're right. Is that right? I think you're right. Sorry. Let's see. Does top k columns of U or top k columns of V? Yeah, I think you're right. Is that right? Something bothers me about that, but I think you're right.
Since U and V are orthonormal, so
Yeah.
then X transpose X should be V D D. Because X is U D V, so X transpose X would be.
Yeah, X transpose X is the, yeah, okay, yes, I think you're right. Cool, thanks. I know. If anyone thinks about it and has another opinion, let me know, but I think you're right. I'll make sure I get the details right and let you know anyway. Okay, so, wow, everyone's still looking at that. Hey, Tom, could you figure out the right answer and let me know?
That sounds right.
He's right? Okay, cool. Yeah. Okay, so just one last note, just sort of a note of caution. It turns out that in this example, I was implementing SVD with a wide matrix. So the matrix X was right, n by n. It turns out when you find the SVD decomposition of this, it turns out that, let's see, yeah, actually, yeah, right, yeah, I think you're definitely right. So it turns out that when you find the SVD of this, the rightmost portion of this block of this matrix will be all zeros. And also, when you compute the matrix D, a large part of this matrix will be zeros. And you have the matrix V transpose, right? And so, depending on what convention you use, for example, I think MATLAB actually uses a convention of just cutting off the zero elements. And so the MATLAB uses a convention of sort of chopping off the rightmost half of the U matrix and chopping off the bottom portion of the D matrix. And so we call, I think this, I'm not sure if this even depends on the version of MATLAB, but when you call SVD on MATLAB or some of the numerical linear algebra packages, there's slightly different conventions for how to define the SVD when the matrix is wider than it is tall. So just watch out for this and make sure you map whatever convention your numerical linear algebra library uses to the original computations. Okay, and so yeah, and it turns out if you use MATLAB or Octave to compute these, or if you're writing C code, there are many scientific libraries like GNU Scientific Library that can compute SVDs for you, but they're just slightly different and consistent conventions for the dimensions of these matrices. So just make sure you figure this out for your package before you use it. Okay. Finally, I just want to take the unsupervised learning algorithms we talked about and so just put a little bit of broader context. And this is partly in response to the questions I've gotten from students just in office hours and elsewhere about when to use each of these algorithms, right? And so I'm going to draw a 2x2 matrix. This is a little cartoon that, I find useful, which is, let's see. So one of the algorithms we talked about earlier, right before this, was factor analysis, right? Which was, I hope you remember, factor analysis was, I hope you remember that picture I drew where I would have a bunch of points Z on the line, right? Then I had these ellipses and I draw, right? I hope you remember that picture. So this is a factor analysis model, which modeled the density of X as a Gaussian, right? We talked about PCA just now. And so difference between factor analysis and PCA, the way I think about it is that factor analysis is a density estimation algorithm. It tries to model the density of the training examples X, whereas PCA is not a probabilistic algorithm. Right? In particular, it does not endow your training examples of any probabilistic distributions, and it just directly goes to find the subspace. So in terms of when to use factor analysis and when to use PCA, if your goal is to reduce the dimension of the data, if your goal is to find the subspace that the data lies on, then PCA directly tries to find the subspace, and I think that would be more. I would tend to use PCA. Factor analysis it sort of assumes the data lies on a subspace. So actually, let me write subspace here. Right. So both of these algorithms sort of assume the data maybe lies close on some low dimensional subspace, but fundamentally, factor analysis I think of as a density estimation algorithm. So if I have some very high dimensional distribution and I want to model P of X, then then factor analysis, the algorithm I'd be more inclined to use. But I would tend not, and so even though you could in theory, I would tend to avoid trying to use factor analysis to identify a subspace that the data set lies on. Okay, so concretely, if you want to do anomaly detection, if you want to model P of X, so that if you have a very low probability event, you can flag an anomaly, then I would tend to use factor analysis to do that sort of density estimation. Okay, so factor analysis and PCA were both algorithms that assume that your data sort of lies on the subspace. The other class of algorithms we talked about was algorithms that assumes the data lies in clumps, so that the data has a few coherence groups. And so let me just fill in the rest of this picture. Right? And so if you think your data lies in clumps or it lies in groups, and if your goal is to do density estimation, then I would tend to use a mixture of Gaussian's algorithm. But if, again, you don't necessarily want to endow your data with any probabilistic semantics, or if you just want to find the clumps of the groups, then I'd be inclined to use the k-means algorithm. Okay, so haven't seen anyone else draw this picture before, but I tend to organize these things this way in my brain. And so hopefully this helps guide, when you might use each of these algorithms as well, depending on whether you believe the data might lie in a subspace or whether it might sort of lie in clumps of groups. Okay, so. All right, that wraps up the discussion on PCA. And what I want to do next is talk about independent component analysis, or ICA. Yeah?
I have a question about the upper right point. So once you have all of the eigenvectors, data set, and you want to know something like, okay, well, how similar is feature I to feature J?
Right.
It looks like, okay, you pick some eigenvector and you take some dot products between the feature I and feature J and the eigenvector.
I see.
But there's a lot of eigenvectors to choose from.
Yeah. Okay. So Justin's question was, having found eigenvectors, how do I choose what eigenvector to use to measure distance, right? So the answer to that is, sorry, my laptop's gone to sleep. Let me just start that waking up first, so while I answer the question. Okay, cool. So the answer is really, in this cartoon, I would actually avoid thinking about eigenvectors one at a time. So a better way to view this cartoon is that this is actually, if I decide to choose 100 eigenvectors, this is really 100D subspace. Right, so I'm not actually projecting my data onto one eigenvector. So this arrow, right, this cartoon, this denotes the 100-dimensional subspace that's spanned by all my eigenvectors. And so what I do is actually project my data onto the span, the linear span of my eigenvectors, and then I measure distance or take inner products between the projections of the 2 points on the eigenvectors. Okay, so cool. Okay, so let's talk about ICA, independent component analysis. So whereas PCA, it was an algorithm for finding what I informally call sort of the quote main axes of variations of data, in ICA we'll instead try to find the independent components of variation of the data. So let's switch to the laptop display, please. So we'll just take a second to motivate that, and I'm actually going to do so by actually you can, yeah, although if you put on the, well, okay, cool, it's on. And so let's take a second to motivate this. This is actually a slide that I showed in lecture 1 of the cocktail party problem, right? Of, you know, suppose you have two speakers, the cocktail party, and you have two microphones in the room hearing sort of overlapping sets of two conversations. Then can you separate out the two original speaker sources? So I actually played this audio as well in the very first lecture, which is suppose microphone 1 records this.
1, 2, 3, 4, 5, 6, 7, 8, 9, y 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, y 10.
So the question is, these are really two speakers speaking independently of each other. It's as if each speaker is outputting a series of sound signals that's independent of the other conversation going on in the room. And so this being an unsupervised learning problem, the question is, can we take these two microphone recordings and feed it to an algorithm to find the independent components in this data, and this is the output when you do so.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
And this is the other one.
1, 2, 3, 4, 5, 6, 7, 8, 9, y 10.
Right, and just for fun, and to give credit to you, these are audio clips I got from Taewon Lee. And just for fun, let me just play the other ones as well. This is overlapping microphone 1. 1, 2, 3, 4,
5, 6, 7, 8, 9, 10.
Right, and here's microphone 2.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
So given those as input, here's our output 1.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
It's not perfect, but it's largely cleaned up the music. And here's output 2. Okay, let's switch back to chalkboard, please. And so what I want to do now is describe an algorithm that does that. So before I actually jump into the algorithm, I want to say just just 2 minutes on CDFs, or cumulative distribution functions. Right. And I know most of you know what these are, but just want to remind you of what they are, which is that let's say you have a 1D random variable S. So suppose you have a random variable S, and suppose it has a probability density function P subscript of S. Okay, then the CDF, right, the cumulative distribution function, is defined as a function, or rather as capital F, which is the probability that the random variable S is, less than the value given by that lowercase value S. And so, for example, right, if this is your Gaussian density, then the density of a Gaussian is usually denoted lowercase phi. This should be set to the 0. That's roughly a bell-shaped Gaussian density. And then the CDF for the Gaussian will look something like this. It'll be the capital function pi. And so if I pick a value S like that, then the height of this, right, this is really the probability that my Gaussian random variable is less than equal to that value S. And in other words, the height of the function at that point is equal to, the area of the Gaussian density up to the point S. And as you move further and further to the right, this function will approach 1, because it's probably because you integrate more and more of this area of the Gaussian. Okay, so Let's see. Right. Yeah. Right. So another way to write f of s is the integral from minus infinity to s of the density dt, right? So something that will come up later is, suppose I have a random variable s, and I want to model the distribution of the random variable s. So one thing I could do is I can specify what I think the density is, right? Or I can specify what the CDF is, right? What the cumulative distribution function is. Because these are related by this equation. F is the integral of p of s. And you can also, recover the density by taking the CDF and taking the derivative. So f prime, take the derivative of the CDF, you get back the density. And so this will come up sort of in the middle of when I derive ICA, which is that there'll be a step where I need to assume a distribution for a random variable s, and I can either specify the density for s directly, or I can specify the CDF, and I'll choose to specify the CDF. And well, what is the CDF? It has to be some function increasing from 0 to 1, right? And so, you can choose any function that looks like that. And in particular, you can, pulling functions out of a hat that look like that, you can, for instance, choose a sigmoid function as a CDF. And that would be one way of specifying a distribution, a density for the random variable s. Okay, so this will come up later. Right. Well, what was I using? Just sanity check. Just raise your hand if all that is familiar to you, if you've seen all that before. Yeah, okay, cool, great, thought so. So let's start to derive our ICA, or our independent component analysis algorithm. Let's assume that the data comes from n original sources. So let's say there are n speakers in a cocktail party, right? So the original sources I'm going to write as a vector s as an Rn. So just be concrete about what I mean by that. I'm going to use Sij to denote the signal from speaker j at time I. Okay, and here's what I mean. So what is sound, right? When you hear sound waves, sound is created by a pattern of expansions and compressions in air. So the way you're hearing my voice is, my mouth is causing a certain changes in the air pressure, and then your ear is hearing my voice as detecting those changes in air pressure. And so what a microphone records, what my mouth is generating is a pattern. I'm going to draw a cartoon, I guess, right, of changes in air pressure, right? So this is what sound is. You look at the microphone recording, you see these roughly periodic signals that comprise, changes in air pressure over time as the air pressure goes above and below some baseline air pressure, right? So this is what the speech signal looks like, say. And so if this is speaker 1, then what I'm saying is that, and this is some time t, what I'm saying is that the value of that point I'm going to denote as s superscript t subscript 1. Okay? And similarly, speaker 2 is outputting some sine wave. If speaker 2's voice looked like that, it actually sound like a single tone, I guess. But so in the same way, at the same time t, the value of the air pressure generated by speaker 2, I'm going to denote as ST2. Okay? So, so we observe xi equals a times si, where these xi's are vectors in Rn. So I'm going to assume that I have n microphones, and each of my microphones records some linear combination of what the speakers are saying. So each microphone records some overlapping combination of what the speakers are saying, right? So, you know, for example, xij, which is, this is what microphone j records at time I. By definition of sort of matrix multiplication, this is sum over ik, aik, sij. Oh, excuse me. Okay, and so what my j, sorry. Okay, right. So what my j microphone is recording is recording some linear combination of all of the speakers. So at time I, what microphone j is recording is some linear combination of what all the speakers are saying at time I, of what, you know, so k here indexes over the n speakers. So our goal is to find the matrix W equals A inverse. I'm just defining W that way, so that we can recover the original sources Si as a linear combination of our microphone recordings Xi. Okay? And, well, just as a point of notation, I'm going to write the matrix W this way. I'm going to use right, so I'm going to use lowercase w subscript 1, subscript 2, and so on to denote the rows of this matrix W. So let's see. All right. So let's look at what ICA is possible. So given these overlapping voices, let's think briefly why it might be possible to recover the original sources, right? And so for the next example, I want to say, let's say that, let's see. For the next example, let's just say that each of my speakers outputs, this will sound like white noise, but let's say, can I switch to the laptop display, please? For this next example, let's say that each of my speakers outputs, you know, uniform white noise. And so if that's the case, these are my axes, S1 and S2. This is what my two speakers would be uttering. And so, you know, the plot of what they're uttering will look like they lie in a square box if the two speakers are independently outputting, you know, uniform -1, 1 random variables. So this is a plot of S1 and S2, my original sources. This would be a typical sample of what my microphones record, where here the axes are X1 and X2, right? And so these are images I got from Apo Haivarinen, so one of the experts on ICA. And so given a picture like this, you can sort of look at this box, and you can sort of tell what the axes of this parallelogram are, and you can sort of figure out what axes, you know, what linear transformation would transform the parallelogram back to a box, right? So it turns out that there are some inherent ambiguities in ICA. I'll just say what they are. One is that you can't recover the original indexing of the sources. In particular, if I generated the data from speaker 1 and speaker 2, you can run the ICA and then you may end up with the order of the speakers reversed, right? Because, and what that corresponds to is if you take this picture and you flip this picture along the 45-degree axis, or this picture, you take the 45-degree axis, you can reflect this picture across the 45-degree axis, and you still get a box. And so there's no way for the algorithm to tell, which was speaker number 1 and which was speaker number 2, because the numbering or the ordering of the speakers is ambiguous. The other source of ambiguity, and these are the only ambiguities in this example, is the sign of the sources, right? So given my speakers recordings, you can't tell whether you got back positive SI or whether you got back negative SI, right? And in this picture, what that corresponds to is if you take this picture and if you reflect it along the vertical axis, if you reflect it along the horizontal axis, and you still get a box. You still get back the same distribution of speakers. And so it turns out that in this example, right, you can't guarantee that you recover positive SI rather than negative SI. So it turns out that these are the only two ambiguities in this example. One is the permutation of the speakers, and the other is the sign of the speakers. Permutation of speakers, there's not much you can do about that. And it turns out that for the signs, it turns out that if you take an audio source and if you flip the sign, if you take negative S and if you play that back through a microphone, it actually sounded it'll sound indistinguishable. And so for many of the applications we care about, the sign as well as the permutation is ambiguous, but you don't really care about it. Okay. Let's switch back to chalkboard, please. So, okay, I won't. It turns out, and I don't want to spend too much time on this, but I'm just say briefly, it turns out that the reason those are the only sources of ambiguity, so the ambiguities were, the permutation of the speakers and the signs. It turns out that the reason these were the only ambiguities was because the SIJs were non-Gaussian, right? And I don't want to spend too much time on this, but I'll just say briefly, suppose my original sources, S1 and S2, were Gaussian, okay? So suppose that SI is Gaussian with mean 0 and identity covariance, right? So that just means that each of my speakers outputs a Gaussian random variable. Then here's a typical sample of Gaussian data, right? And you may recall the contours of a Gaussian distribution with identity covariance looks like this, right? The Gaussian is a spherically symmetric distribution. And so if my speakers were outputting Gaussian random variables, then if I observe a linear combination of this, there's actually no way to recover the original distribution because there's no way for me to tell if the axes are at this angle or if they're at that angle and so on, because the Gaussian is a rotationally symmetric distribution, and so I would not be able to recover sort of the orientation of the rotation of this. Okay. So I don't want to prove this too much. I don't want to spend too much time dwelling on this, but it turns out that if your sources are Gaussian, then it's actually impossible to do ICA. And ICA relies critically on your data being non-Gaussian, because if the data were Gaussian, then the rotation of the data would be ambiguous. And so regardless of how much data you have, even if you had quote, infinitely large amounts of data, you would not be able to recover the matrix A or W. Okay? So let's go ahead and derive the algorithm then. And to do this, I need I need just one more result, and then the derivation will be 3 lines. So I have these random variables Sn, which is the joint vector of the sound that all of my speakers are emitting at any time. And so let's say the density of S is P subscript S, capital S, right? So my microphone recordings records, X equals AS equals W inverse S, or equivalently S equals W times X. So let's think about what is the density of X. Right? So I have P of S, I know the density of S, and X is a linear combination of the S's. So let's figure out what is the density of X. One thing we could do is, figure out what S is. So this is just apply the density of S to W of S, right? So let's see, this is the probability of S, and so we just figure out what, figure out what S is. So S is W times X, and so the probability of S is W times X, and so the probability of X must be equal to that, right? So this is wrong. It turns out you can do this for probability mass functions, but not for continuous densities. So in particular, it's not correct to say that the probability of X is, well, you just figure out what S is, and then you say the probability of S is applied to that. So this is wrong. And you can't do this to densities. You can't say the probability of S is this, because this is a probability density function. And in particular, the right formula is the probability of density of S applied to W times X times the determinant of the matrix W. And let me just illustrate that with an example, which is, let's say the density for S is that. So S, in this example, S is uniform over the unit interval. And so, the density for S looks like that, right? It's just a uniform, this density for the uniform distribution over 0, 1. So let me let X be equal to 2 times S. And so this means A equals 2 and W equals 1/2. So if S is a uniform distribution over 0, 1, then X, which is 2 times that, will be the uniform distribution over the range from 0 to 2. And so the density for X will be that's 1, that's 2, and that's 1/2, and that's 1. Okay? And so density for X will be indicator 0 less than equal to X less than equal to 2 times W times 1/2. Okay? And so, does that make sense? And so, to actually compute the density for X, because X is now spread out, across a wider range, the density of X is now smaller, and therefore the density of X has this 1/2 term there. Okay? And I guess this is an illustration for the case of one-dimensional random variables where S and X are 1D. I'm not going to show it, but the generalization of this to vector value random variables is that the density of X is given by this times the determinant of the matrix W, where here I showed the one-dimensional case, which is a generalization. Okay. So we're nearly there. Here's how I can implement ICA. So my distribution on S, right? So I'm going to assume that my density on S is given by this is a product over the n speakers of the density, the probability of speaker I emitting a certain sound. This is a product of densities. And this is a product of distributions because I'm going to assume that the speakers are having independent conversations. So the SIs are independent for different values of I. So by the formula we just worked out, right, the density for X will be equal to will be equal to that, where just remind you, W was A inverse. It was this matrix where it was this matrix I defined previously, so that SI equals WI transpose X, right? So that's what's in there. So to complete my formulation for this model, the final thing I need to do is choose a density for what I think each speaker is saying, right? I need to assume probably just some density over, the sounds emitted by an individual speaker. And so following the discussion I had, right when I was starting to solve for ICA, one thing I could do is I could choose the density for S, or equivalently, I can choose the CDF, the cumulative distribution function for S. And in this case, I'm going to choose a cumulative distribution function. And so maybe partly for historical reasons and just partly for convenience, I need to choose the CDF for S. And so what that means is I just need to choose some function that increases from 0 to 1. And well, what can I choose? I know I can't choose a Gaussian because we know Gaussian, you can't do ICA on Gaussian data. So I need some function increasing from 0 to 1 that is not the cumulative distribution function for Gaussian distribution. So what other functions do I know that increase from 0 to 1, right? Well, so it's just convenient to choose the CDF to be the sigmoid function. Okay, and this is a commonly made choice that is made for convenience. There's actually no great deep reason for why you choose a sigmoid function. It's just a convenient function that we all know and are familiar with that happens to increase from 0 to 1. And when you take the derivative of this, right, you take the derivative of the of the sigmoid, and that will give you back your density. And this is just not Gaussian, because that's the main virtue of choosing a sigmoid. So there's really no deep rationale to the choice of sigmoid. Lots of other things will work fine too. But it's just a common reasonable default. Let's say this. All right, fine. It turns out that one reason the sigmoid works well for a lot of data sources is that if this is the Gaussian, and if you actually take the sigmoid and you take its derivative, you find that the sigmoid has fatter tails than the Gaussian, by which I mean the density of the sigmoid dies down to 0 much more slowly than does a Gaussian. So for Gaussian, the magnitudes of the tails dies down as e to the minus s squared. Whereas for the sigmoid, the tails look like e to the minus s, sort of asymptotically. So the tails die down as e to the minus s around e to the minus s squared. And it turns out that most distributions with this property with fatter tails, where the distribution decays to 0 relatively slowly compared to Gaussian, will work fine for audio data. Okay. So actually, one other choice sometimes uses what's called the Laplacian distribution, which is that. And this will work fine too for many data sources. But sticking with the sigmoid for now, just write down the algorithm in 2 steps, right? So given my training set, and as usual, this is an unlabeled training set, I can write down the log likelihood of my parameters, right? So that's, the sum of my training examples, log of times that. So that's my log likelihood. And so to learn the parameters W of this model, I can use stochastic gradient ascent, which is the usual right, which is just that. And it turns out if you work through the math, let's see, if P of S, right, is equal to the derivative of the sigmoid, then if you just work through the math to compute the partial derivatives there, and you've all done this a lot of times now, so I won't bother to show the details, you find that is equal to this. Okay, and that's just, you can work this out yourself. It's just math to compute the derivative of this with respect to W. And so to summarize, given a training set, here's my stochastic gradient ascent update rule. And so you run stochastic gradient ascent to learn the parameters W. And after you're done, you then output S I equals Wxi, and you've separated your sources, your data back out into the original independent sources. Hopefully up to only a permutation and a sign, plus minus sign ambiguity. Okay. So just switch back to the laptop, please. So let me just wrap up with a couple of examples of applications of ICA. Cool. This is actually a picture of our TA, Katie. So one of the applications of ICA is to processing various types of brain recording data, so EEG, MEG data. This is a picture of a EEG cap in which there are a number of electrodes placed on the well, in this case on Katie's brain, on Katie's skull. So where each electrode measures changes in voltage over time, measured on the scalp. And so on the right is a typical example of EEG data, where each electrode measures just changes in voltages over time. So the horizontal axis is time, and the vertical axis is voltage. And so here's the same thing blown up a little bit. And you notice there are artifacts in this data, like that where the circle is, where the data is circled, all the electrodes seem to be measuring these very synchronized recordings, right? And it turns out that when you look at EEG data, as well as actually a number of other types of data, there are artifacts from heartbeats and from human eye blinks and so on. So the cartoon is, if you imagine that placing a number of electrodes, or microphones on my skull, then each microphone is recording some overlapping combination of all the things happening in my brain or in my body, right? So it's as if my brain has a number of different processes going on, my body has a number of different things going on, and each microphone or each electrode measures a sum of the different voices in my brain. Although that didn't quite come out the way I wanted to. So, so what you can do is take this data and run ICA on it and find what are the independent components, what are the independent processes going on in my brain. This is an example of running ICA. And so you find that there's a small number of components like those shown up there that correspond to heartbeat, right? Where the arrows, so those are very periodic signals that come on, occasionally that correspond to sort of roughly 2 components of heartbeat. You also find things like eye blink, an eye blink component corresponding to the signal generated whenever you blink your eyes. And by doing this, you can then subtract out the heartbeat and the eye blink artifacts from your data and now get much cleaner ICA data, get much cleaner EEG readings that you can do sort of further scientific studies on. So this is a pretty commonly used preprocessing step that is common application of ICA. So one quick example is the application of, this is again from Apohai Varonen, was a result of running ICA on small natural image patches, which is suppose I take natural images and I run ICA on the data and ask what are the independent components of images. It turns out that these are the bases you get. So this is a plot of the sources you get. And so this algorithm is saying that, you know, a natural image patch, this is from a student Hong Lak Lee, natural image patch shown on the left is often expressed as a sum or a linear combination of independent sources of things that make up edges. And so this model's natural images, you know, is generated by independent objects that generate different edges in the image. And one of the fascinating things about this was that, so in neuroscience, this has also been hypothesized as a method for how the human brain processes image data. And this turns out to be, you know, similar in many ways to computations happening in early visual processing in the human brain, in the mammalian brain. And these has also, and it's just interesting to see edges are sort of the independent components of images. Okay. Other quick questions? So I'm running late. Quick questions before I close? Yeah.
Do you assume A is a square matrix?
Oh, yes. For the algorithms I described, I assume A is a square matrix. It turns out if you have more microphones than speakers, you can also apply very similar algorithms. If you have fewer microphones than speakers, it's sort of an open research problem. State of the art is that if you have one male and one female speaker, but one microphone, you can sometimes sort of separate them because one is high, one is a low voice. If you have two male speakers or two female speakers, then it's beyond the state of the art now to separate them with one microphone. But it's a great research problem. Cool. Okay, sorry about running late again. Let's close now, and we'll continue with reinforcement learning.